welcome back. Today is day 7 of our Polynomial Functors course. Unfortunately, I don't have as much of an audience today due to various COVID restrictions in the Berkeley area. We are kind of limited on our ability to host people here, but that means that my audience is you folks at home, so that still works for me. So yeah, today we're going to talk about a particular construction in Poly that's very closely related to our composition product, and it helps us think about our dynamical systems in a slightly more coherent way. And then it's going to turn out that this particular structure turns out to just be small categories. And yeah, and we'll see all that entire story today. Oh, one other thing, because of the new restrictions, I have to wear a mask now, but it's a little, I'm still getting used to like talking through this, so hopefully things will still be okay, but excuse me if things sound muffled. Yeah, so let's start by looking at an example dynamical system. And remember, the things that we're calling dynamical systems are these morphisms from sy to the s to an arbitrary polynomial p. And what that does is it assigns each state in S, each element of S, to a position in P. And then once we hit a position in P, we can take one of the directions in P, send it back to get another element of S. And so here's an example. We let S be a 2-element set with red circles and blue squares. And we let P have positions U and V. At U, the directions are A, B, and C. And at V, the direction is just this star. And the particular morphism, the particular dynamical system we're going to look at, is depicted by this picture here. It's going to send the circle state to the output U. It's going to send the square state to the output V. And at the output U, you have possible inputs A, B, or C that lead you either back to the red or over to the blue. And I've colored these arrows with the color of their target. So it's whichever state the arrow leads to. And similarly, if you start at, if you're at state V, if you're at state square, your output is V, so your only possible input is star, and we're going to say that star sends you back to the circle state. Okay. And now we're going to, we can also draw this as our Corolla picture, right? So we have the system where you can start at this at the red circle, output U, maybe input C. You're at this blue square, output V, input star, and then so on. You can sort of traverse the system like this. We can also draw this out in as our Corolla picture. So sy to the s has 2 roots and 2 arrows coming out of each root. And I've colored, again, I've colored this with a red, this root with a red circle, this one with a blue square. And then these are going to be.
No sound.
Oh, just completely?
No, someone else. David has no sound. Someone else says it.
Huh. Is the little meter going up on the?
Yeah, it says.
Okay. Okay.
Go
Okay,
ahead.
there should be. Okay, I'm going to keep going then. Hopefully, sound can get figured out. Yeah. Let's see. Right. So, so this root here is being sent over here, and then each of these arrows coming out is colored by the arrow that it leads to over here. So, for example, if we started at the red circle state, we would output U here. And then our choice of possible inputs are either A, B, or C. A is going to lead us to this red arrow here. Picking B is going to lead us to this red arrow, and picking C is going to lead us to the blue arrow. Okay, but now what? Right, so we ended up at maybe this red arrow or this blue arrow. And now we know that this red arrow in some sense corresponds to this state, and this blue arrow in some sense corresponds to this other state. But how does Poly know that, right? We said that these are going to be the same sets. We kind of know that kind of in our heads. And we could say that, okay, yeah, we kind of know that in our heads that this arrow is associated with this state, and then this arrow is associated with that state, and so on. But is there some way the structure of this polynomial itself, is there something we can add to this that like keeps track of that information, and actually lets us travel back and forth through here? Put another way, really what this is doing, this morphism, when we go forward and then go back once, it really just tells us how to perform one step of our dynamical system, right? It tells us how to get from one state to an output, from an input back to one of the arrows coming out of that state. But it doesn't tell us, and we can sort of manually like run this multiple times, but the information contained here doesn't sort of automatically give us a way to actually run this system. And so I guess what I'm trying to get at is that there's something extra about the structure. There's some additional structure that we want to add to this in order for us to be able to talk about maybe going through the system twice, back and forth, or 3 times, or so on. And so let's try to think what we're missing. Well, we need some way to associate, to like tell sy to the s, to tell this polynomial that this red arrow means this state. Similarly, right, like this blue arrow is talking about, is referring to this state. And so we need some way to associate positions of sy to the s to directions of sy to the s. Well, what's a way that we know how to associate positions with directions? We've talked about one way to do that, and it's a situation. So this is going to be our first attempt here. Attempt number 1 to sort of address this kind of like missing structure here. Let's give a situation on sy to the s. So this is sy to the s. And a situation, if you recall, is an arrow into y, which is a single root with a single leaf coming out of it. And what that does is everything, all the positions go to this corolla, but then this arrow is going to specify one direction or the other at each position. And so the way I'm going to write this is that I'm going to say, okay, at this position, the direction coming out of it that gets specified by the situation is going to be this one, because that's the arrow that's tied to the red position. Similarly, for our second position, the direction we're going to pick is this one. That's the arrow that's tied to this position. And so now at least we know which direction actually means stay here, right? Like which direction tells us to stay at that position. Unfortunately, that's not quite enough, right? We also need to somehow tell sy to the s that this direction is associated with this state, that this direction is associated with this state, and not this position, right? And if we had more positions, right, here we have s equals 2, but if we had maybe like 3 or 4 positions, we would have a bunch of arrows where we didn't know which arrow was associated with which position, at least not through just a single morphism like this. But that's a first step. That's maybe a small step, so I'm going to call this arrow epsilon. And let's see what else we need to do. So we need some way of going from here from sy to the s forward to p, and then back, and then forward again, and then back. And we kind of talked about a way of doing that last time, I think last time I spoke, which is by taking two morphisms and composing them. So this is going to be our second attempt at talking about actually running our dynamical system, actually running through it multiple times, which is that, well, we can think of running through the system, let's just say twice, as going from, let's see, yeah, as going from sy to the s, composed with sy to the s, to p composed with p. And remember, a morphism like this tells us a way of going forwards from sy to the s to p, then backwards on the directions. But then at that direction, we're going to have another position of sy to the s that's sent to another position of p over here. And then that's going to be sent, a direction there is going to be sent back to a direction there. So that's going to let us go through here twice. That's where the position product is so useful. So what specifically do we want going on here? Well, let's think about this. So let's take one of our positions of sy to the s over here. And again, so the original map is just the original map phi. Right, so this is going to be, in some sense, phi composed with phi, or the composition product of phi with itself. This gets sent over to the three arrow state. Got too many markers here. The three arrow state, the three arrow position, sorry, of p composed p. Okay. Now, what we want is for each, so we know each of these red arrows gets sent to this red arrow, and this blue arrow gets sent to this blue arrow. And what we want is, if we're at this red arrow, to go back to the red position. Right, so then we're just going to have this again. And similarly, if we're at the blue arrow, we want it to go back to the blue position. Or not go back, but go to the other position, which is the blue position. Which is going to look like that again. And so now, once we've gone through here once, we're at a new position, the position that we wanted to go to. And we're going to send that forward again through the map phi. And that's going to give us this particular position of p composed p, which you'll recall is just a position of p and another position of p attached to each direction at that position. Okay, and then picking a direction there tells us which direction over here we want to go to. You can see based on the colors. And then that's great. That's exactly what we wanted. We wanted to run through this system twice. Okay, but we also need to know what happens if we start at the blue state. So I'm going to draw this a little bit quickly here, because we've already seen this once. And here, the particular position we're going to pick is the one that actually assigns the right positions to the right directions here. And that gets sent over here to something that looks like this. Okay, great. And that tells us, now we have a morphism that tells us how to get, how to go around the system twice. But you'll notice that there's actually a lot of extra information going on here, right? We didn't have to attach this red dot to this red arrow or this blue square to this blue arrow. There's a bunch of other positions of sy to the s compose sy to the s that are kind of like pointless to us. Like we only want the ones that are sort of compatible like this. And so really what we're doing, we only really care about these two positions. And so what we're really doing is actually composing this with another morphism from sy to the s that has the right number of positions, right? These are the only positions we care about. One for what happens if we start at the red dot, and one for what happens if we start at the blue square. Okay. And is this the type of thing we really want? Well, if we go backwards on directions, what is this saying? It's saying that, well, we can kind of decide what it says. And one sort of reasonable thing, I am handling too many markers here, but one reasonable thing to say is that if we travel maybe from a red to a blue here, a red and then a blue, well, we end up at the blue state. And so really this should end up with the blue arrow, right? Like we should, if we do a red and then a blue, that should take us back to the blue arrow. If we do maybe a blue and then a blue, that should also take us back to the blue arrow, and so forth. And so really the key thing that's kind of helping us here is this arrow from sy to the s to sy composed with sy to the s. Sorry, sy to the s composed with sy to the s. Great. Now what we've really done is we've kind of sped up the system, right? So now what happens, because we've created this new system, right, that it's a morphism from sy to the s to p composed p. So this is actually a new system built from our old system that has as its states the same states, but now has its interface this kind of like two-step process of the original interface. And so now each state gets sent to this like big state of like things you can do in 2 steps rather than just things you can do in 1 step. And then if you do 2 steps of this, going backwards along this morphism, it's going to tell you where you're going to end up, not just after 1 step, but after both steps that you do. And so that's what this morphism tells us. Great. Okay. This is cool, but there's another like slight problem here. I don't really know. Yeah, maybe it's a problem. This delta that we've picked here, I called this delta, this map from sy to the s to sys, compose sy to s. It needs to satisfy some certain properties. It can't just be any map this way, right? We need this bottom part to actually match up with this bottom part to actually like demonstrate this like 1 tree growing into 2 trees. We need, let's see, we need the do nothing arrow, right? Like remember that this red arrow should take us from our red state, red position, back to our red position. We need this do nothing arrow to actually have a red dot on top of here, right? Like we need to actually pick the red dot there. Fortunately, we kind of know how to do this through our sort of sy to the s to y morphism here. We know which arrow is going to keep us in the same position. But so somehow this delta and this epsilon need to talk to each other in a certain way. And finally, there's one other thing that would be nice for delta to do, which is that it should. We want to be able to talk about taking even more steps, even more than just 2 steps. If we talk about taking 3 steps, I'm going to move over here. If we want to take 3 steps from sy to the s, if we want to get to sy to the s composed with itself 3 times, we want to be able to, there's kind of 2 ways to do this, right? Like you could either go to sy to the s, compose sy to the s with delta, and then split up this second thing again. So this is really sy to the s composed with delta. Here I'm just using the sy to the s to mean the identity arrow from sy to the s to sy to the s. Or we split it once and then actually split the second thing here. And we want those two ways of splitting this to sort of be the same, right? Like we don't want there to be, right, there's really only one way to take 3 steps of the system. And so we want this to be compatible in a certain sense. There's some kind of like associativity law going on. But once we do solve all these issues, if we can find a nice map delta that has all these properties we want, we should be able to give these arbitrary maps from sy to the s to, I'm going to use this kind of special notation here, p to the power of like n with this little triangle here to mean p composed with itself n times. And so we can just keep applying delta to sy to the s. Oh, sorry, actually, no. I didn't want to write p here. I wanted to write sy to s here. But still, this is going to be n copies of this. We want to use delta to build up these like bigger maps that we can then feed into p composed n, p composed with itself n times, by applying our, composing phi with itself n times. And once we have maps of this form, we can construct this larger dynamical system that tells us how to get from how to take n steps of this original system. Okay. Yeah, and that, yeah. And so one example of this, one sort of special case of this is if n is 0, this is going to be a map from sy to the s to y, because if we think about it, y is our unit for this composition product. And so when n is 0, so an empty composite is just going to be our y. And this is actually just the epsilon map we had, because this tells us what happens if you take 0 steps, right? If you take 0 steps, you're still in the same state, which is the map that we wanted that tells you which arrow keeps you in the same state. Okay, I just said a lot of stuff to sort of set this up. This is where I would normally pause for questions. Feel free to put something in the chat, but I'm going to take a drink of water. So you can tell probably at this point that there's something I'm teasing here with all of this, which is that there's this particular structure. There are these particular properties that sy to the s satisfies that lets us add this extra structure on it. A map from sy to the s to the monoidal unit, to y, and from sy to the s to sy to the s composed with itself, this delta here, in a certain compatible way. And in fact, the compatible way we're going to want to do this, I'm just going to put this up here, is encapsulated by this definition of a comonoid in our category. Now, comonoids can be defined in any monoidal category, but I'm specifically going to tell you what it means in poly here. We're going to have a some particular polynomial, which we call the carrier. We're going to have a map from that carrier to the monoidal unit, to y, which we call our co-unit, which you could also think of as like a deletion operation. You're kind of getting rid of C. And then another map from C to C composed with C, which we call co-multiplication, and we label with the delta. We can also think of something like duplicating C. And this is going to need to satisfy certain laws. I really should call these the left co-unit law and the right co-unit law, maybe the co-associative law, but just too many co's to keep track of, so I'll just write it like this. But essentially what this says is if we start here, we use delta to split C up, to duplicate it, but then if we delete it on one side with epsilon, we should still get the same C. And similarly, if we delete it on the other side with epsilon, we should still get the same C. Down here, this is exactly saying what I said up here. So if we take C, if we split it up one way and split it up another way to get 3 C's, it should be the same as the other way we can split it up to get 3 C's. Now, this kind of definition should probably be familiar with you, to you if you've seen monoid objects in a category before. For example, monoids in set just follow this exact definition, except with all of the directions of the arrows flipped, which is exactly why we call this the co-unit and the co-multiplication, because it's just kind of like the opposite of a multiplication map and a unit map for a monoid. So that's where all the names come from, and you can see this is a really natural notion to be dealing with. And yeah, let's see what these things actually say about our sy to the s here. Let's see. So let's take as an example, what do I want to do? Yeah, let's take as an example one of the positions of our sy to the s polynomial, where s is this 2-element thing. Yeah, I'm just going to erase this. Actually, I'll keep this because it's, maybe I shouldn't have erased. Okay, I'll keep this down here, but let's see what this unit law says. Okay, so it's saying that we're just going to focus on one position. It's saying that if we start at this red, then blue, and we perform this duplication map down here, which attaches all of this stuff, this red thing here, and a blue thing here. If we do this duplication, but then we do a certain deletion on one side or the other, well, so our epsilon map, what's this going to do? So let's make this epsilon composed with the identity. So our epsilon map is going to take this and tell it which direction it corresponds with. And remember, this is the red position, so it's going to correspond with the red direction. So we're just going to take that red direction, but then it's composed with the identity, so it's just exactly a copy of what's already up there. And so the position that it gets sent to is this, which you can see does in fact correspond exactly with this. It's just, if you collapse this down, this just becomes this, and that's exactly what our left unit law is saying. In other words, on positions, what this side is saying is that you should make sure to attach yourself, right, because these two are equal, to this arrow here, this arrow that is, in some sense, the do-nothing direction. Meanwhile, over here, we are applying the identity composed with epsilon, so it's sort of the other way here. And that's going to bring us to, that's going to make us pick these do-nothing arrows up here. And somehow collapsing this down should be the same thing down here. And you can see that this is still true. And what this law says on positions is that whatever this is should be the same thing as whatever this is on the bottom here. So that's exactly this thing we had here, where we want to keep the same thing on the bottom. But these both also say something on directions. And what it's saying on directions is that if we pick any one arrow and then pick the do-nothing arrow, this is going to go back to just the same blue arrow. Similarly, if we pick the do-nothing arrow and then the red arrow, that's going to take us back to this red arrow. And so there's some sense in which this is behaving like identities. That's exactly how identities work. And in fact, I can draw out what the associative law says. And there's something, it's going to be saying on directions exactly that the way we follow these arrows, follow three arrows, is going to be associative if we collapse it down to one. And this probably is all starting to sound very familiar. And it should not surprise you, because I've already given it away, that these comonoids are actually, where do I want to put this? I'm just going to put this here, actually. These comonoids are actually just categories. And here I've written up a chart of exactly what's going on here to tell you how to go from a comonoid to a category and vice versa. And okay, so what I'm saying, I'm telling you that these comonoids are categories. I haven't really told you what the category is. It's going to turn out that these dots that we've been drawing on the bottom, all of these positions of S, Y, to S, are just the objects of the corresponding category. And the arrows coming out of it is exactly what this picture suggests. It's the morphisms coming out of those objects in the category. And so this tells you at least sort of all the data you need to get a category, actually get a comonoid from your category, right? If we have a category, the corresponding comonoid, the carrier of the corresponding comonoid, the positions of that carrier are just the objects of the category. They're just all these little dots that we've been drawing. Whereas the directions of the carrier are going to be the morphisms coming out of that position. So a direction F of C at I is a morphism F from the position / object I. It's a morphism out of it. Now I've drawn this blank here because there's some, in some sense, this doesn't tell us where these arrows end up yet. There's something else we need to give it, but before we give that, I'll point out that the co-unit, remember the co-unit is a map epsilon from C to Y. It doesn't really do anything on positions because everything gets mapped to the same position, but on directions, remember this is a, it's basically, it's a situation, and so it's going to give every position I a direction in that position, at that position. And so remember, our directions are our morphisms, and so the direction specified is going to be our identity morphism coming out of I. And so that's the do-nothing arrow that I've been talking about, this, the red arrow for the red dot and the blue arrow for the blue square. And then delta is going to give us all of the other data for this category. On positions, our co-multiplication on positions is going to tell us what the codomains for these morphisms are, because we haven't told you those yet. And really what that's saying is that's how we attach these, this second level to this first level. Whichever position we pick to attach to this arrow is going to be the target of that arrow in our category. So the position we pick for here is going to be the codomain of this arrow. The position we pick here is going to be the codomain of that arrow. And that's how delta on positions is giving us these codomains. Meanwhile, on directions, what it's saying is that if we take one arrow coming out and then another arrow coming out, and we follow those two arrows, that's going to be sent back to an arrow coming out of our original position here. And so that's going to tell us how arrows compose, how each pair of arrows compose to one arrow. And so that gives us all of the data we need for our category. Meanwhile, all of the laws, all of the comonoid laws are going to correspond to certain laws for our category. And you're going to see that this is just going to be a one-to-one correspondence. And how do we check all these laws? Well, we can do these with our polybox notation. Let's see. I think I'm going to erase this. Erase this, and then take another sip of water while you can look at this and sort of preview how these laws are going to work out. OK. So we have a co-unit, epsilon from C to Y. And if we draw this out as polyboxes, what's happening is it's one box here where we get to pick the position that goes here. Remember, positions of C are just objects of our category. And that's going to be sent to a position here. However, Y only has one position. So I'm actually going to just color out this square because this choice is automatic. There's not really any choice going on here. There's also not really any choice going on up here. Usually this would be something you got to choose. But there's only one direction up here, and that's going to send us back here. I'm going to call this, let's call this H for now. And so you can see that this is a quick way to draw that this kind of morphism from C to Y, this position, is really just an arrow going like that, right? It just takes each position of a position of C to a direction at that position. And if you will recall, I said that these co-units on directions are identities. And so I'm just going to call this ID sub I. And maybe whenever this arrow shows up, I'll label it ID to remind you that it takes an object to its identity. That's the co-unit. What does the co-multiplication do? Well, it's a map into a composite, which makes it really nice to draw with our polybox notation. And so it's this kind of thing where we get to pick a position here, and that's an object in our category C. It's going to be sent down to some position here. And since this is delta, I'm just going to call this delta I for now, although we'll see very shortly what this has to be. Then we get to pick a direction at this position. That's a morphism coming out of this object delta I. And up here, that's going to give us a position associated with this direction. So an object associated with this morphism of the category. And we claim that this map is really the codomain map, taking any morphism F to its codomain, an object of the category. Then, from here, we pick another morphism from this codomain F, and the result, we claim, is going to be the composite of these two morphisms. So this f and g are going to be sent over there here to f composed with g. And we're using the semicolon to note f composed with g. Now, okay, let's see what the laws say, because there's something a little tricky going on here. So let's see what the laws say. Well, the right unit law, we'll start with the right unit law, and you'll notice that I've marked that the right unit law on positions actually helps tell us the codomains and the composition. And this is why, on positions, what the right unit law is saying is, let's see, let me just fill this in. The right unit law says that if we start from C, we duplicate it to CC. I'm saying right, but really, since we've oriented this whole thing upwards, it's like the upwards unit law. And so once we attach epsilon over here by drawing this identity map here, this is going to send codomain of f to, let's see, is this what I want? Yes, to identity of codomain of f. And over here, it's going to end up as, let me just write it outside because this box is a little small. It's f composed with identity at codomain of f. And what the law says is that this is equivalent to the identity, which is just a map from C to itself, sending I to I and sending F to F. And now we can start matching things up. Okay, so I here gets sent to delta I, whereas here I get sent to I. And so that tells us that actually delta I is just I. This is the thing we saw earlier with our sy to the s, where our delta map is going to keep the thing on the bottom the same. It's going to keep the same position on the bottom. Okay, so now I'm just going to replace this with I. We know that this is just an equal sign now. This is just the identity. It's always going to send I to I. What's this saying on directions? Well, if we plug in f, after going through this long chain of things here, the direction we end up here, the morphism coming out of I, is f composed with the identity of the codomain of f, which over here is f. And so this tells us our expected right identity law, that f composed with the identity on the codomain of f is f itself. Okay. Taking a look how much time I have. Okay, I think we can keep going. Let's see. Okay. I'm actually, let's see, I think this should be, hopefully you got the idea of how we did this. I'm going to leave the left identity law as an exercise for you to try out yourself. It's going to be the same idea as this, except we're putting this deletion, instead of putting it here, we're going to put it down here. And so you can try to draw this out and read off what this equation is going to say. You're still going to have this identity on C on the right-hand side here, but you're going to move this down here. And it's going to turn out, you should be able to check this, that the left unit law on positions is going to tell you that the codomain of the identity is what you would expect. It's the object itself. And the left unit law on directions is going to tell you that composing with the identity on the left also gives you the same thing. Okay. I'm going to bring us all the way over here to draw out what the associative law says, which is a little bigger. Because if you look at this, the associative law, we have these sort of two maps here, two ways of doing delta twice. And so one way of doing delta twice, let's see, which one am I going to draw first? I'm going to draw actually this top way first. So we start from our, let's see, I'm going to make this box rather wide if I want to fit everything in here. Okay, we're going to start with C here. Duplicate it once with delta to get 2 C's. Remember, this is an equal sign. This is codomains, and this is composition. Then we're going to duplicate the bottom again. And then keep the top the same. So it's really just the identity on the top here. Okay. Okay, now if I had an audience, I would make you participate. But what we're going to start with is we got a choice of what position to pick here, what object of our category to pick here. Through delta, that's going to be sent to itself. Now down here, that's still going to be sent to itself because it's just delta again. And now here, we're going to get to pick what morphism comes out of I, which one of the morphisms coming out of I. So let's say we pick F. We're going to follow this up here to go to the codomain of F. Then we get to pick a morphism coming out of the codomain of F, which we'll call G. And then this composition is going to compose these two to get F composed with G. That's going to be sent up here to the codomain of F composed with G, which is just going to be sent to itself over here through this identity. And then we're going to be able to pick a direction up here to, let's see, a direction up here. Again, this is just the identity to that same direction up here, and that's going to be sent composed. So we're going to compose, let's see, we're going to compose this down here with this, because that's what this delta is saying we should do. F compose G with H. So that's going to be F composed with G composed with H with the parentheses like so. Now, let's do the other direction. Let's see if I can fit this all here. I'm going to start drawing it over here just to make sure I can fit in all this. Okay. The box is bigger. Nope, that should go this way. Okay. So we're going to start over here. We're going to pick a object of our category. We're going to send it down here through delta to the same object, I. Then here, this is just an identity. So this gets sent to I. We can pick any of the morphisms coming out of I. Let's say F. This gets sent to F over here. This is the codomain map, which we're going to send to the codomain of F, which is going to go through another delta over here, which is the identity at least over here. From here, we pick a morphism coming out of the codomain of F. Let's call it G again, because that's the same name we gave it up here. We're going to come up here. This is the codomain map. It's going to send G to the codomain of G. We pick another morphism coming out of it. We're going to call H, just like up there. And that's going to be sent over here to G composed with H. And finally, this composition map is going to compose F with G composed H. Okay. So what is this whole thing saying? if these two things are equivalent? Well, on positions, it's saying that this object I is being sent all the way through all this stuff to here. So we're sending the object I over to the codomain of f composed with g. Down here, we're sending I all the way through here to here. No, not yet. To here. That's where we end up, codomain of g. And so what this says on positions is that the codomain of g is just the codomain of f composed with g, which is kind of obvious with categories, but which isn't information that was encoded in the polynomial itself, right? We have to tell it what codomains are and how codomains are compatible with composition. Okay. Now, on directions, this is just the associative law. It's saying that f composed with g, all composed with h, is the same thing as f composed with g composed with h. Okay. And that's how we get all the laws we expect of our category from the equivalent laws over here of our comonoid. Okay, I'm going to pause for a little bit so you can digest this, and in case there are any questions that come through. Oh no, that's unfortunate. Where did it freeze? Did we get all of this?
It froze just a little bit.
Okay. Okay. Cool. Okay, we're back. Great. Okay. Let's see. I'm going to use these remaining, I think, like 3 minutes to give a couple of examples of categories viewed as these comonoids. We've already seen an example. S-Y to the S. Erase this. Already seen S-Y to the S, which, let's think about what kind of category this is. This has S many objects. And again, let's actually let S be 3 this time, just for variety. Has S many objects, with 3 objects, and out of each morphism, out of each object, there are 3 morphisms. And if you think about the kind of pictures we were drawing, the morphisms are going to go to every other object. So there's an identity morphism to itself, and then there are 2 more morphisms, 1 for each of the other objects. And so we can fill all these in, and what we see is that this is kind of like a very generic state system. In fact, it is a state system. It's a state system where like all of the transitions are possible. There's only one transition you ever care about between any 2 states. Yeah, and composition works like, the way composition works is that we really only care where we end up. So if we went from here to here, it's really just the same thing as going here without worrying about where we went through. And so if you think about sort of the category theory of this particular category, it's, in fact, all of these objects are isomorphic to each other, because if you follow any of this arrow and then back, it has to be the same as the identity, because those are the only arrows there. And so this is what's called a contractible groupoid. A groupoid because all of the morphisms are isomorphisms, and it's contractible in the sense that there's really only one isomorphism class. The only thing setting it apart is how many states it could have. Okay. Here's another category. We're gonna go pretty straightforward today. Imagine your sort of first category theory class, but taught with these polynomials instead. One of the simplest kinds of categories is a discrete category, where all of the morphisms are just identity morphisms. And so all of the objects form a set, which we can call S. And each object only has one morphism coming out of it. So this is just SY to the 1, or just SY. And you can see that, as expected, there's only really one morphism from SY to Y, which identifies all of the identities. And composition is this particular map, which is saying, and this is equivalent to just a map from S to S squared. So the co-multiplication is really just equivalent to a map from S to S squared. And it's going to turn out that this is just the diagonal that sends each little s to the pair S comma S. And if you'll recall, this tells us, this always is just S, this is just itself, but this tells us what the codomain of this particular morphism is. There's only ever one morphism, and it's the identity, and that has to be, the codomain of that, based on our laws, has to be the identity. So everything's really decided already, and that's the structure of our discrete category. Another very simple kind of category is, let's see, sorry, I should write. This is discrete category. Another very simple category is the monoid, which is just a one-object category. Now, these are monoids in set. So, just one object category with a binary operation, let's see. So you can either think of it as just a one-object category, or you can think about it in terms of the set of morphisms on that one object, with composition as the binary product that is associative and unital. So it is a monoid in set. I'm just going to call the set M. And, well, the multiplication is just morphism compositions. I'll still use that symbol, and the identity is just the identity morphism. And if this has one object, that means that this is a monomial, and it's a monomial with no coefficients. It's just one position, and the directions are all the morphisms, so that's just the entire set M. Okay. And so what's this? Well, we have to have a co-unit that's mapped from Y to the M to Y, but that's just, there's nothing on positions, there's no data on positions, and it's just a map from 1 to M backwards on directions. Well, this just specifies the identity. Meanwhile, the co-multiplication is from Y to the M to Y to the M composed Y to the M. But that's just Y to the M, which is Y to the M squared. And so this is just a map from M squared to M. We don't really worry about codomains here because there's only one object. So this is composition. This is the monoid, the monoids product. And yeah, and so those are some very straightforward examples. One thing to notice here is that the polynomial itself doesn't really give all of the data we need for the category. Just the same, for the same reason that, or for a similar reason that, if you just draw a picture of a category, you don't necessarily know all of the composition structure yet. So this is just a particular point of view of the category that tells you how many objects there are and how many morphisms come out of each object. At least that's what the carrier tells you. You need to know what the co-unit does to find the identities, and you need to know what the co-multiplication does to know how morphisms compose and codomains. Yeah, but you can create any category like this, and any comonoid is going to give you one of these categories up to isomorphism, and that is it for today. I hope you got something out of this, and yeah, thank you for coming. Feel free to ask questions in the chat. Thank you, David, for the applause. Yeah.
Nick Smith says, thank you, very good talk.
Yes, thank you, Nick. It's always good to see you. Yeah. In the chat. Okay. If there are no other questions, we'll probably end the live stream in a couple seconds. Thank you so much. See you Monday.